Okay, today we're going to focus on Newton's third law of motion. So Newton's third law of motion is the easiest of all three of his laws, and it's the one that's the least mathematical, but also the one that's also confused at times because of how we sometimes view things. So Newton's third law focuses on the interaction between two objects when forces are applied. So understand that a force, a push or pull that acts on an object, but it's always one object acting on another. So let's say that I were to pull something, it's me pulling on that object. So it's an interaction between two things. Any force always occurs between two objects. So what Newton's third law looks at is the forces between those two objects. And the key way to understand Newton's third law is based on what's called an action and reaction. Okay, so you might know Newton's third law is that for every action there's an equal and opposite reaction to it. But what this is talking about in terms of forces is that when one object applies a force on another, like for example, this guy applying a force on the wall, that at the same time he pushes on the wall pushes back on him. So there's a force against his hand that's pushing back on him. Okay, so forces always come in pairs. Then anytime you have two objects interacting with each other, that there's a force applied to one object, and then there is an equal and opposite force applied back onto the first. So the key thing here is that if this guy is pushing on the wall, let's say 20 newtons of force, that the wall is pushing back on him with the same amount of force. Okay, so for every action, for every force, there's an equal and opposite reaction force to it. So we can look at all these examples. For example, like this guy hits the punching bag. So that would be a force. So the reaction force to that would be the punching bag would actually hit back on his hand. Same thing here. So if I have this blue object that collides with the yellow, that while the blue object hits the yellow, at the same time the yellow hits back on the blue. So again, it's all about this idea of action versus reaction. So the way to think about this is that we have two objects. I'll label this object 1 and object 2. Okay? So the action in this case would be the force of 1 onto 2. I'll just write it like that, F of 1 comma 2. All right? So that would be the force of object 1 hitting object 2. So I'll draw that with an arrow. But at the same time, there is also a force of the second object back on the first object. I'll write that as F of 2 comma 1. And this force I would draw with an arrow on the blue object going back in the opposite way. Now I want you to notice the two diagrams where it says equal and opposite. So what it tells you, what Newton's third law states, is that these two forces in magnitude would be equal. Okay, so if this force, let's say, just making up a number, was 20 newtons, then this would be 20 newtons. But you can see that the force on one object is the opposite direction as the force on the other. Okay? Now this gets a little confusing at times. It's easy to understand, I think, to understand the whole idea of action-reaction pairs. But where this gets confusing is the whole idea of action and reaction versus cause and effect. So cause and effect would be what happens to each of these objects. So for example, the blue object hits the yellow. Now what happens to the yellow? So obviously the cause is there's a force. It's experiencing a push. And the effect is that yellow object is going to be set into motion. So that's cause and effect. Whereas this force, when the yellow hits back on the blue, what does that cause the blue object to do? It causes that to come to a stop. That's the effect. So there's a cause and effect on each individual object with this action-reaction pair. But the forces that they exert on each other are always equal and opposite, even though the cause and effect might be different. What I mean by that is one object was set into motion while one object came to a stop. So cause and effect is going to be different than action and reaction. Now to help understand this is we're going to talk about and focus on this idea of what's called a system. So this is a fancy science word for representing the thing or things that we are interested in. So let's say I look at the objects, the blue object and the yellow object that are colliding with each other. There are essentially three ways I can define a system. I can identify the forces acting strictly on the blue object. I can identify the forces strictly on the yellow object, okay? Or I can look at the forces that act on both objects. So when I identify a system, I can identify this, let's say, as system A. This could be system B. And then this could be system C. So I can consider looking at the forces of one, the other, or both objects. Now let's see how this applies to Newton's third law. So let's say that I have an apple pulling on a cart. There are essentially three ways in which I can define the system. The first way I can define the system is let's say just look at the forces acting on the orange. So if I identify the forces acting on the orange, I would have the force of gravity, say the normal force, I would have a pulling force, and then I would have the frictional force back that way. Okay, so those are four forces acting strictly on the orange. But I could also look at the forces acting strictly on the apple. So I have the normal force again, gravity, this tension force pulling back, and then since he's pulling forward, there's probably an applied force causing him, as he's walking, pushing himself forward. Okay, now notice these forces are not the same, all right? Where I have here gravity acting on both, but the weight of each object is different. I have the normal force, but again, acting on two different objects. I have an applied force forward versus friction, but the one force that is the same, and I'll draw these together, is if I consider the forces acting on each of them, again, I have gravity acting for both, normal force acting for both, I have an applied force forward and friction backwards, but I do have the force of the apple on the orange and the force of the orange back on the apple. And this idea right here, this would be what's called the action and reaction pair. Okay, because I have the two forces acting on each other, but one is the force of the apple on the orange, and the other is the force of the orange back on the apple. And the key thing here about Newton's third law is that these two forces are equal in magnitude and opposite in direction. Okay, so now let's focus on this idea of action and reaction. So in the diagrams, the arrows are going to represent the action and the reaction. So this first one, let's just say we have a ball being dropped from that looks like the Leaning Tower of Pisa. So we'll just say that the ball is falling. Now, why does the ball fall? Well, the ball falls because the earth, the earth pulls the ball. All right? Now, the reaction to that is maybe different than what you might think. When we think, okay, the action is the earth pulling the ball, a lot of people think the reaction is that the ball is going to fall. But that's the cause and effect. What the reaction is to this is that the ball is going to pull back up on the earth. So the way I like to think about this is caveman talk. Earth pull ball, ball pull earth. Okay? Now, cause and effect is different. Earth pulling on the ball is going to cause the ball to fall. The ball pulling on the earth, all that just means that the ball is pulling up on the earth, that technically the earth should move upward, which obviously it doesn't, and we'll talk about that in a little bit. But the whole idea of action and reaction is that one object acts on the other, the reaction would be the other acts on the first. So second object, I have a man and a spring. So I'll say here the action would be man pulls spring, otherwise that spring wouldn't stretch. And again, the effect of that would be that the string stretches, but the reaction to this would actually be the spring pulls the man. Each of those, again, have a cause and effect relationship, that this one would cause the spring to stretch. This one would stop the man from falling. Next one, I have a rocket and some gas. So I would say here that the rocket, I'll just think pushes and pulls, so I'll say here pushes the gas. So the reaction to this would be that the gas pushes the rocket. Okay, cause and effect again is that the gas will be shooting backwards and the rocket will be pushed forward. And that's actually how rockets and such are launched into space, and that's how they work in space. Last one here, we're focusing on this wheel. So we're looking here at the point of contact between the wheel and the ground. So I'll say here that the wheel, this is kind of how friction works and how things move, the wheel pushes the ground. So the reaction to that would be that the ground pushes the wheel. And again, cause and effect here, when the wheel pushes the ground should go push backwards. And at the same rate, the ground pushes the wheel. So what ends up happening here is this is how you walk. This is how cars move. That essentially when we push off the ground, that we're technically pushing into the ground. And the only reason why we move forward is that the ground also pushes us forward. So it's actually the ground that's propelling us and this car forward because of this action and reaction pair. All right, so what I want you to do here is I want you to pause the video, give these a shot. So notice I'm not giving you the arrow, but in each of these situations should be kind of easy. But think about what would be the action and reaction pair. So go ahead and write those down, pause the video, go for it. Pause it, do it. Okay, take a look. So the first one, I have a hammer and a nail. So I said hammer hits nail, nail hits hammer. A lot of people get confused with B, but that's a boat and a dock, and there's some water. So I said girl pushes boat, jumps off boat, boat pushes girl. Okay, that's why the boat would move backwards and she would move forward. She looks perplexed because is she actually going to make the dock? Who knows? Then we have truck hits car. Reaction would be car hits truck. And if you said that backwards, doesn't matter. Now, number D here, this one's a little sassy because we have 1, 2, 3 objects. So Newton's third law always acts with 2 objects. So I would have here, I chose one example. I said A hits B and B hits A. Okay, so there are other ways to do this last one. I could say B hits C, C hits B. I probably don't want to say A hits C and C hits A because they don't technically interact with each other. They both interact with B. Now, one thing that sometimes people do incorrectly on this one is they'll say that A hits B and B hits C. It's a little math property called the transitive property, but this idea right here, this example does not actually work out with Newton's third law because Newton's third law only looks at the interaction between 2 objects. Okay, last example here, this is the idea of the whole cause and effect. So again, action and reaction is pretty simple to understand, but where we sometimes get confused is the idea of cause and effect. That Newton's third law states that whenever 2 objects interact, the forces on one are equal to the forces on the other, but we sometimes don't understand this because we see what happens to these objects. So for example, let's take the example of a bug smacking the windshield of a bus. Okay, so it says use Newton's laws to describe why the bug goes kasplat and the bus goes vroom. So just to simplify this, I'm going to label the bug with a lowercase b and the bus with a capital B. So here's what Newton's third law states, is that the force of the bus on the bug equals the force of the bug on the bus. That these 2 forces are equal and opposite, okay? Again, so if I were to draw this with a blue arrow, that the bus is going to apply a force forward on the bug, and the bug is going to apply a force backwards on the bus. And that these 2 forces are equal and opposite, equal in strength and opposite in direction. Now here's the only thing. Cause and effect tells us this, that when the bug hits the windshield, the bug goes kasplat. So what we naturally think, that if a bug goes kasplat, that the force that the bus applies on the bug is much, 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 much bigger than the bug applying a force on the bus. So this gets a little confusing, but the forces are always equal. Now what we're going to use is that what this relates to is Newton's second law of motion. So why, in this case, if the forces are equal, why does the bug go kasplat? So here's the idea. The forces are the same, okay? So the force of one is going to equal the force of the other. But what happens here is that if I think of the bus, I'll use the bus on the left side. The bus has a huge mass compared to the bug, which has, compared to the bus, a very tiny mass. Now what that creates then is that if I take, for example, this is the bus, and I take that force of whatever that value is and I divide it by a huge mass, I'm going to get a very small acceleration, okay? But if I take that same force and divide it by a very, 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 very small mass, I'm going to get a huge acceleration. Okay, so this goes back to the whole idea of mass being an inverse relationship with the acceleration. Our acceleration is our experience of a force. So the bigger object is not going to experience that force as much, even though the force is the same. But because it's got more resistance, that force is not going to have as much of an effect on it. Versus if I have a bug which has a very tiny mass, that same amount of force is going to have a much drastic effect. Okay, the same example could be seen with a recoiling gun. Okay, so a recoiling gun, if you ever have shot a gun before, that it launches a bullet outwards and that gun experiences a recoil. Recoil, they sometimes say, would be like a kick, that the gun is going to basically shoot back into this person's shoulder. Now the reason why that is because of Newton's third law. That let's just say I draw this as like a rectangle. What ends up happening is that as the bullet is launched outward, okay, that it pushes the bullet outward, but at the same time, Newton's third law tells me that as the barrel shoots out the bullet is also going to apply a force backwards on the gun. Now here's the idea, is that the force of the gun on the bullet are going to be equal to each other, okay? But what happens here is that the bullet is so small that that same force divided by a small mass is going to create a huge acceleration. And that same force applied to a much larger mass is going to create a smaller acceleration. So that's why we see a slight recoiling of the gun, is because the gun is not extremely massive, but it does have some mass that it's going to kick back a little bit because of Newton's third law, that if there's any force due to the mass, it's going to experience some acceleration. Which is also why they tell you to hold that thing tight against your shoulder, because when you hold that thing tight against the shoulder, you also add your mass to it, which is going to make that acceleration even smaller. So again, just focusing on Newton's third law, the idea of action-reaction and differing from cause and effect.